Hi customer service agents, it's Sarah again. This is the third presentation out of 4 regarding the maternal and paternal lineages. And this is a map of the maternal haplogroups and their migration patterns, which I will be discussing later in this presentation. So let's get started. If you guys recall from the very first presentation on cells and DNA, DNA is found in 2 places in a cell. The first place was the nucleus, where we have the 23 pairs of chromosomes, 1 pair being the sex chromosomes, and that's where the Y chromosome lies in terms of the paternal ancestors. And then the other place DNA was in the mitochondria, and this where we get the maternal ancestor side. So, if you recall, this is the only organelle where DNA is found, and in terms of the DNA, there are 16,500 base pairs. The nucleus had over 3 million base pairs. And in terms of genes, mitochondria, 37, and the nucleus over 20,000. So the sizing is completely different. Mitochondria DNA is passed on from mother to her children. So a son would have the same exact mitochondria DNA as his sister, as well as they would have the same mitochondrial DNA as their mother, who has the same mitochondrial DNA as her mom, and etc., etc., etc. I mean, obviously mutations happen, but we'll get to that. So you may be wondering, why does mitochondria have its own DNA? It's the only organelle. That's odd and interesting at the same time. What's going on? Scientists believe in a theory called endosymbiotic theory. It happened billions of years ago, and what happened was a cell consumed another cell, most likely a bacterium, because mitochondria DNA resembles bacterial DNA, so that's a safe assumption. Again, this is a hypothesis, and they had a mutual relationship where they benefited from one another, and it just maintained over time. This is very similar to the classic relationship of a clownfish, Nemo, and the sea anemone. So the clownfish is protected by the sea anemone, which sings, so it doesn't get eaten by other fish. At the same time, the clownfish protects the sea anemone from other fish that will eat it, because clownfish are very territorial, as well as they provide nutrients in the form of poop, and they clean the sea anemone. So this mutual beneficial relationship isn't new. Organisms do it today. Another question you might be asking is, why does mitochondria only pass through the mother? Well, sperm does have mitochondria. It requires a ton of energy to get to the egg. So what happens to it? They actually recently just found out by studying roundworms that the sperm and mitochondria self-destruct as soon as it pierces the egg. And this prevents it from being associated with the new baby, the formation of the egg and the sperm. And then when it self-destructs, a vacuum comes through and cleans it up. So the evidence is gone. But this is how they believe that only maternal mitochondrial DNA is passed on through organisms. Now, all of that aside, mutations. So just like DNA in the nucleus, mitochondrial DNA goes through mutations. It has a mutation rate that is very small, very similar to the Y DNA. It's 1.66 times 10 to the negative 8th. And if you don't like the scientific notation, I'm not going to say 0.00000 forever, so you can see it there. Very similar to Y DNA, these mutations or mutation brings about different haplogroups, different subclads. Maternal haplogroups are 36 to 42, and this naming is very similar. The letter, capital letter A, B, whatever, number, lowercase letter. The only thing that's a bit different is haplogroups for maternal was named as they were discovered, whereas Y DNA, you start off with A, B, C, and as they branch off, it's more of a pattern versus the maternal DNA. For example, Y chromosomal atom, it was an A, whereas the mitochondrial Eve for women is an L, and she came about like 200,000 years ago, whereas the Y chromosomal Adam came about 275,000 years ago. So you can see the difference in time, as well as that concept of the first man and woman. By evidence, they lived 75,000 years apart. So again, keep that in mind. Phylogenetic tree, very, very, very similar to the Y-DNA one. You have a haplogroup, mutations occur, you get a new haplogroup subclad, same thing. If you look at these two that diverge from A2, this one's A2AD, A2AF, and this one, A2AD, came about from 16,000 years ago, and A2AF is from like 24,000 years ago. So again, it takes thousands of years, they're all branching off, and through this you can see the migration patterns. Perfect. So through these mutations of in mitochondrial DNA that we can see in fossils, as well as them living today, we find the migrations patterns. So we have in this phylogenetic tree, we have N, when N2 became a W, and then N1 became an N1A1B, which became an I. And you can see through these migration patterns, N to W, N to I. Now this is really nice. This sets all three up. So you have the phylogenetic tree, the migration pattern, as well as the heat map, which, if you recall, is the frequency of a haplogroup in an area. So in this phylogenetic tree, we have the haplogroup N, which then had a mutation and became R, which then had a mutation and became JT, which then had a mutation and became J or T. And then the same goes for HV mutation, another mutation, you got H, and then you got a V. And you see through migration pattern, N, R, H to V, R, J to T. And if you look at this heat map, majority of the people of the H1s are found in the Scandinavian region, which is what we presumed based on the migration pattern. You think more people with that haplotype would have went that way. So this is a picture of, not a picture, it's a table of, very similar to the Y-DNA, of all the haplogroups, the year, and then the origin. And you can see haplogroup L, which is the original, the mitochondrial Eve, happened about 150 to 200,000 years ago and originated also in Africa. So just like Y-DNA, maternal DNA does have its limitations and issues. If you remember, for Y-DNA, haplogroup T, how many reports we had to do to include every subclan for every consumer or every person that we know now. It's very similar to maternal DNA. Haplogroup G, if we want to do every subclad that is known today, it'd be over 60 reports, and that's just for one haplogroup. We do have limited research in terms of qualifications to be considered a subclad. Ancestral information or migration patterns are not also known for everyone. But again, with technology and the science and the interest, this is growing rapidly, and time will tell and give us more information. And very similar to males, female haplogroups may not move out of the area or enter the area. And this, just like males, Oceania is just a really good example of haplogroups that formed there, and they didn't really go anywhere. But again, keep in mind, like I mentioned in Y-DNA, scientists are looking at indigenous populations, specifically in South America, and they're finding that though we all thought everyone came through Russia into North America, this may not be quite the case. So I guess that's a fun thing about science, is you always are learning something new always finds out. And in this aspect, you're finding out something about your ancestral past, which is really cool. In terms of markers, we use 136 to determine one's maternal haplogroup. And this is just an overview picture. Can I move my face? I'll move my face so you can see both. Just to give a comparison of the maternal and paternal haplogroup migration patterns, the years, where they originated. You can see that mitochondrial Eve is here, and then mitochondrial Adam, or y-DNA Adam, is here, and the different times they've appeared. And this just gives you an overview and helps you understand the time it takes for mutations, how long they've been around, where you fall in this, as well as the difference between the maternal and paternal aspect. So, thank you again. This is the third presentation, and you luckily only have one more to go of listening to me talk. So, thanks guys, and see you in a little bit.